or the scientific method, and equipping students with the tools to fight science disinformation, as well as the protection of scientific heritage. He has received a number of national and international distinctions recognizing his contributions to both research and outreach, as well as 4 honorary degrees. He currently chairs the steering committee of the annual UNESCO International Day of Light, a global outreach action that has seen over 3,000 events take place in more than 100 countries since its first celebration in 2018. And this was a direct legacy action of the International Year of Light, which again, Ghana played an incredible role and a very critical role in seeing that proclaimed. And I just want to add that both John and I are friends of Francis, and we say friends instead of, I could have said colleagues, but if you look at his smile, it was infectious. So anybody that met Francis was automatically a friend. And I think he had a very effective way of dealing with interacting with everybody that he met, and you just couldn't say no. So anyway, the title of John's talk, now that we've kept him waiting, is Quantum Light, the International Day of Light, and the International Year of Quantum Science and Technology. Okay, John, we're going to play your video, and then John's sticking around to answer some questions afterwards. Okay, let's go.
It's a tremendous pleasure and honor for me to be with you today as part of the celebration of the International Year of Quantum Science and Technology, and to be delivering this FKA Alote lecture. In this talk, I'd like to go through 2 main themes. The first is a general presentation of different science outreach activities in collaboration with UNESCO, and the second, which is a more scientific-oriented talk on some stories from the history of quantum mechanics and the lessons that we can draw from these today. It's over 10 years that the international community working in photonics and light science has been working with UNESCO on science outreach initiatives. This began around about 2013, 2014, when we first made contact with UNESCO in Paris and the Ghana National Commission for UNESCO to approach the United Nations General Assembly with an idea to propose 2015 as the International Year of Light. That was a tremendous success, which saw over 13,000 events take place around the world, reaching a worldwide audience, estimated at several hundreds of millions of citizens and students around the globe. And since 2018, we've been annually celebrating the theme of light and light-based technology through the International Day of Light, which in the 8th edition so far has seen over 3,000 events take place. Professor Francis Alote was key and central to both of these initiatives. He was a keen supporter of the International Year of Light. He worked tirelessly to negotiate the complications of bringing the science and the diplomacy communities together. And he spoke on the 19th of February 2015 in Paris, as many of you will remember, delivering a wonderful speech about the importance of international science, communication and education to Africa. In 2017, only a few weeks before he died, I met him in Paris as we were preparing for the UNESCO General Conference that was considering the final endorsement of the International Day of Light resolution. In 2015, in Africa and in Accra in Ghana, the Ghana National Commission organized an African regional conference and exhibition on harnessing light and light-based technologies for African development. And this was held in September, and you can see Francis front and centre in that photograph, along with several others who I imagine are also in the audience today. And this conference really highlighted the importance of photonics and photonic-related technologies in driving development on the continent, and it essentially prepared a roadmap which is still underway today in both research, education, and in public engagement. The date of the International Day of Light, which is now held every year, is the 16th of May, and this date is chosen because it corresponds to when the laser was first observed to oscillate by Ted Mayman at a 693 nanometers from a ruby laser. And what's important about the laser as something to remember is because the way in which it developed brings together so many aspects of contemporary science: international cooperation, curiosity-driven fundamental research, and applied development in industry, as well as many unexpected applications of basic research and the way that lasers were found to find uses that no one who initially worked on their development had ever envisaged. And reminding ourselves annually of this story is extremely important in the present time as we try to advance science for the benefit of humanity. Francis understood this very well because he had himself worked on several aspects of laser physics during his career. And in preparing this talk, I was absolutely delighted to read this paper, which was actually performed relatively late in his career, around 2003. It just shows us how active he was scientifically throughout his entire period of work at universities with ICTP and with other national and international partners. The aim both of the International Day of Light as well as the International Year of Light and the International Year of Quantum Science and Technology is to focus on the goals of the United Nations relative to sustainable development. I'm guessing that for this audience you'll all be very aware of these 17 goals. You'll be aware of the many successes, but also how far away we are from really achieving the ultimate objectives and how much work there still is to do. Photonic and quantum science can contribute together to achieving these goals, and during this conference you will see some specific examples of technologies and applications that directly respond to many of these objectives. The success of the International Year of Light actually has helped in the creation of broader outreach activities with UNESCO. We have assisted in other international years since 2015. We worked together with the organisers of the International Decade of Sciences for Sustainable Development, which has very broad goals and provides an overall umbrella for work in science cooperation for the next several years. And again, I'd like to thank the Ghana Commission for UNESCO, and especially Rich Mike Wellington, who played a crucial role in mobilizing and coordinating the various partners to successfully take the resolution for the International Year of Quantum Science and Technology to New York and the United Nations General Assembly. Anyone who has ever tried to do this realizes just how difficult it is. And there's an enormous amount of work, and the role of Ghana in driving this initiative is extremely important to recognize and thank. So thank you once again. Without your help, we wouldn't be here today. One of the interesting things about working together with UNESCO is that it's not just about the scientific community performing outreach activities. We have a great deal to learn from UNESCO as well. And UNESCO is a remarkable organisation that often conducts its activities, in my opinion, without giving them the publicity they really deserve in reaching out to the scientists who need to understand them. So one example of this is the UNESCO Science Report, which is a remarkable 5-year monitoring document, which is really unique in assembling data from all sorts of sources. The last report was in 2021, the next is scheduled for next year. And just to give you an example of the kind of information that it would present, it presents trends in publishing, funding, patenting, and summarises activities for specific countries, across specific regions, and so forth. So even the 2021 document is well worth looking at, and we should look forward next year to the upcoming report. We cannot do better than the phrase of Nelson Mandela, reminding us of the importance of education in driving change. The world is clearly in a complex place at the moment, and we need education more than ever. And I think we can be very hopeful that if we take this message on board and we continue to work together, then we can really affect positive change in the future. And so this is something that I personally try to remember whenever we struggle with these issues of communication in science, and we get a little bit upset by how sometimes our actions don't seem to be as effective as we'd like them to be. But we need to be optimistic, and we need to transfer that optimism to the next generation, because it's really the young people of today who will be driving the future of this planet. And so we need to help them as much as we possibly can. In order to help them, as well as to help ourselves, we need to understand science and its history perhaps a little bit better than we actually do. And this is where international years provide a great way for us to spend time talking about the history of our own discipline. It's always difficult to know where to start a historical talk, but let me begin with a nice picture of a phenomenon which we've all seen and which has presented itself as a symbol across cultures as well as religions, and from a scientific perspective, its study has been at the heart of the quantum revolution. The study of light and how it's composed and its spectrum has truly revolutionized physics. It was, there have been many proposals for trying to understand how rainbows were formed, for example, but it was really only with Newton that we developed a more quantitative picture of how white light is composed of a series of different colors. Now, Newton proposed splitting the spectrum up into 7 colors, but this was completely arbitrary because it's a continuum of colors, from violet to blue to green and yellow and orange and so on, up to red. But it was in the 19th century when there was a discovery looking at the spectrum of the sun in more detail that it actually wasn't continuous, but it was punctuated and crossed by a number of dark lines. Now, this is a hand-drawn picture from Josef Fraunhofer in the Deutsche Museum in Munich. And you can see that the different colors are labeled with letters of the alphabet, A, B, C, D, etc. And for those of you who have done spectroscopy, you'll know that we still refer to particular lines by these letters, the sodium D line, for example. The reason these labels were used was because at the time Fraunhofer made the picture, there was no widespread agreement on how to measure light in terms of wavelength. It was only just before Fraunhofer's observations that the quantitative ideas of the wave theory of light had been proposed by Thomas Young and Augustin Fresnel. And of course, there are many other figures shown in the slide and names from different countries who have been involved, but it was really as a result of this quantitative theory that it was possible to perform an interference experiment, and based on the measurement of spatial fringes in an interference pattern, infer the nanoscale wavelength of the light that was generating the pattern in the first place. I don't think we appreciate just how remarkable this is, that by measuring something on the scale of millimeters or centimeters, we can infer a dimension of a light wave of the order of 600 nanometers or so. Now, Fraunhofer did better than Newton in replacing his prism eventually by a device which we now know as a diffraction grating, which uses interference phenomena to create some very well-defined peaks that allow us to separate white light spectra very precisely with high resolution into its constituent components. Now, this technique had actually been discovered a bit earlier in the United States, and even earlier than that, in the 17th century, it had been reported fortuitously by James Gregory by looking at light through a feather. If you happen to see any feathers on the street around the conference centre, pick them up and have a look at a point source through them, and you'll see that a feather acts as a very effective diffraction grating. And just while we're at it, it's worthwhile remarking that this idea of seeing colour in natural objects is a wonderful way to talk about light to students. It's called structural colour, and it allows you to introduce the ideas of light, wave theory of light and so on, even quantum concepts, in a way that ties back to the natural world. And since this is a talk about science communication and outreach as well as history, I can't resist just showing you a photograph from my own office of a very inexpensive toy that I purchased a while ago, which is just a very basic USB microscope that you can connect to a computer. Such a device gives you 10 microns resolution, which is wonderful to use when you're carrying out outreach activities with young people. So if you haven't got one of these in your labs already, I strongly recommend that you pick them up, because it's a tremendous value for money in terms of the way it inspires young people. Now, Fraunhofer, returning to the history, Fraunhofer had discovered dark spectra in the solar, dark lines in the solar spectra. Around 1859, Kirchhoff and Bunsen made the observation that when they heated certain salts, crystals, metals in a hot flame, they would see bright lines emitted using a spectroscopic apparatus, with some of these bright lines occurring exactly at the position where Fraunhofer had seen the dark lines in sunlight. And that was again a remarkable observation, because it pointed out that using this tool of spectroscopy, we are able to identify elements that we see on Earth present in gaseous phase in the atmosphere of the sun. This led to a more detailed study of these bright lines in different systems from solids and gases. And there was a great deal of interest in studying the spectrum of the lightest element of hydrogen, because this was known to emit 4 very bright lines that were known by their alphabetic names as well as by their wavelengths. However, there wasn't any theory describing where these numbers came from, but it was a mathematics teacher, Balmer, in Switzerland, who discovered a mathematical formula known as the Balmer series describing where these lines were positioned. But Balmer was not a physicist, he was a mathematician. He did not have any theory underlying where this formula came from. It was just a mathematical fractional proportionality sequence that he had discovered in trying to fit the lines the position of the lines that were observed. Meanwhile, as well as the study of these discrete spectra, these discrete lines, work was also being carried out elsewhere in Europe, studying continuous spectra. Now, by a quirk of physics and physicists wanting to make things seem perhaps a bit more complicated than they are, a physicist would call a bright continuous object like the light bulb or the sun, we call it a black body, which is a rather strange name. It refers to its absorption characteristics, but this is a terminology one sees in all the literature and the history on the subject. And studying this black body radiation was extremely important in the development of quantum mechanics, but what people don't often recognize is that the reason that the physicists like Wien and Planck were driven to understand the spectrum in detail from a heated object was because of a very practical question raised by the city of Berlin that was in the process of deciding whether to illuminate the town streets by gas or electricity in the 19th century. So they had to make the discussion, as we do today, whether we on the kind of efficient light sources we use when we're designing new buildings or new urban infrastructures. It's exactly the same decision. But at that time, they had no benchmarks to consider. They had to perform the measurements of the spectra from different light sources. And that was the time when the first high precision measurements of artificial spectra was made. And that revealed a discrepancy between the 3 main theories of how the discrepancy between the different theories that had been developed over the years to model continuous light spectra. This is a technical slide for the experts, but basically it shows that the one model due to Rayleigh genes fitted the experimental data very well at long wavelengths. Another, due to Wien, fitted it very well at shorter wavelengths, but it took Max Planck to find the correct model that fitted the experimental data across the full wavelength range from the ultraviolet to the infrared. But to do that, he had to assume that energy was quantized, that the energy exchange between the radiation field and the emitting body did not occur in a continuous way, but it occurred in discrete steps, or quanta. So that was the first, around 1900, was the first idea that physics required quantization to explain the properties of light. In 1905, Einstein added to this by using the idea of light quanta to explain another phenomenon known as the photoelectric effect. And this is a phenomenon that occurs when light or electromagnetic radiation, as shown in the picture, hits a metal surface and it causes electrons to be emitted. This is essentially the phenomenon at the basis of all photovoltaic energy sources today, and it's one that has been extensively studied ever since. But the basic idea of requiring quantization to see this emission and to explain the experimental results in terms of the photocurrent observed as a function of light frequency and intensity, that was explained by Einstein in 1905, and it was for this that he was explicitly awarded the Nobel Prize. Five years after Einstein's paper on the photoelectric effect, as well as his other papers in that very famous year of 1905 for Einstein, there were discussions about holding a special conference to discuss the theory of light and quanta. So this is the name you'll see in the proceedings that were given to this conference. The conference was held in Brussels at the Metropole Hotel, and it was really the first international conference on physics or any other discipline that ever took place. It was around the beginning of the 20th century that there was a possibility of travel, whether by boat or by train, to bring scientists from different countries together to one location to share all their ideas and exchange their exchange and debate in one place, face to face. And it was this Solvay conference, which was held in 1911, that really formed the basis of the scientific workshop that we still use today. Now, Francis understood this, and he organized many, many conferences. There's a wonderful article that he wrote in 2017 where he gives a retrospective on Abdus Salam and ICTP and how important he found ICTP in supporting activities in Africa, particularly the many workshops that he himself would organize. And I can't resist showing the photograph on your right, which is my own introduction to ICTP in 1991, when I attended from New Zealand a winter college on ultra-fast phenomena. And so the arrow's pointing to me on the right up the back there, but on the left there's another arrow pointing to Paul Pasteur, and it was Paul himself who played an equally important role in the proclamation of the International Year and Day of Light by being part of the UNESCO delegation and speaking at some of the important commissions where the resolutions were first proposed. And of course, together today in Accra, you are yourselves taking part in a very important workshop itself. So we all inherit this tradition of scientific workshops, which date back to the need of physicists to get together and to understand quantum mechanics in 1911. 2 years after the Solvay conference, Niels Bohr published a very important paper where he developed, finally, a physical model that explained, that derived from first principles, the formula for the 4 spectral lines in the hydrogen spectra that Johann Balmer had obtained mathematically. And Bohr's article is wrong. So physicists are known for being direct, and so we have to say this. From a 2025 perspective, Bohr's paper, if you read it, is extremely strange. There was a 2018 article in the Physics Teacher that describes some of these aspects, but it predicts things that are incorrect, such as the orbital angular momentum of the ground state. It predicts it to be finite when in fact it's zero. And it brings together classical and quantum ideas in a very strange way. But it worked. It predicted the Balmer series based on physical principles, and in trying to correct the Bohr model and to put it on more solid foundations, it was the later scientists that developed the more rigorous theory of quantum mechanics that we enjoy today. Now, what's important about the Bohr model is that it really provided, if you like, the end stage of 99 years of study of the solar spectrum. From Fraunhofer in 1814, observing dark lines, to the observation of bright lines, by Balmer's formula, by the idea of quanta, to Bohr's model, which builds on all of these things. We see the progression from experiment to explanation. But this tells us something. Science is hard. Science takes time. It took 99 years between seeing Fraunhofer lines and having any kind of atomic model to describe where they came from. It took 27 years between the time that Balmer derived his formula and Bohr explaining where it came from. And this is a lesson for today. Science takes time, and it requires long-term support. If you look at a picture like this, and you consider the funding duration of a typical 2025 science project, it's maybe a very small fraction of this timeline. We fund projects for 12 months, maybe 36 months. If you're very lucky, you'll have a 5-year project. But when you look at how long science really takes, it's clear that this, in my opinion, is very, very far from satisfactory. A little observation I'd like to point out as a slightly frivolous one is the fact that Balmer, after he derived his formula in 1885, no one knew where it came from. Niels Bohr was born in 1885. So it was almost as if the universe was saying, I've given you all these clues about quantum mechanics, you're not figuring it out, so I'm going to create Niels Bohr. Bohr will be born, and his entire life will be spent at the age of 27, he'll derive the Bohr model. When I was involved with the European Physical Society a few years ago, I was asked to write a paper summarizing different research models, and this was published in Nature Photonics. And it's the paper itself is not very original at all. It just brings together ideas about how different kinds of research interact. And the references in this can be very interesting if you haven't heard about these different models before. And I'm happy to give you a copy of this paper if you can't find it yourself. So heading back to the history once more, we jump ahead. We've got the Bohr model in 1913. 3 years later, Einstein developed a rate equation model for how atoms and photons, using the modern vocabulary, interact and undergo population and energy exchange, still introducing a notation of coefficients which he called A and B that we still use today when we teach laser physics. And the laser physics pioneers won the Nobel Prize in 1964 for the work that predates the observation of the laser light by Ted Mayman, but which was awarded for the principle of the maser and the laser combined. Again, continuing the history, a few years later, Louis de Broglie, I guess reminded us that quantization per se is actually a classical phenomenon. So we see quantization whenever a wave is confined by boundary conditions. Anyone who's played a musical instrument knows this. So the fact of confining a string at its ends necessarily creates only certain frequencies that are allowed to oscillate. And so this concept of quantization is not new to physics. But what de Broglie realized was that when we see quantization on the microscopic atomic scale, this implies that, in a sense, the electrons around a nucleus are displaying wave properties. And this led to the whole concept of wave-particle duality, which is one of the key concepts of quantum mechanics. 2 years later, we saw the development of rigorous mathematics. So this is 12 years after Bohr's very approximate quantum theory, we start to see the quantum theory we use today. And it's these papers which first started to appear from 1925, which motivate the anniversary of the International Year of Quantum Science and Technology being held this year. So these papers were published by Max Born, Pascal Jordan, Werner Heisenberg, Erwin Schrödinger, and they start to show the differential equations or the matrices that we use today in which we teach to our students. Now, this differential equation form of the Schrödinger equation was used by Francis Allotte during his PhD thesis. And one of the wonderful things I discovered in preparing this talk was I read through Professor Allotte's PhD thesis paper. And it's a wonderful work on scattering resonances and X-ray emission. And in the acknowledgements, I was extremely surprised to read that he thanked a certain J.J. Hopfield. And this is the same John Hopfield who won last year's Nobel Prize for developing concepts of neural networks and artificial intelligence. Before John Hopfield moved into artificial intelligence, he worked in quantum physics and many other areas of physics. And I, on the off chance I did not expect a reply, I wrote an email to Professor Hopfield 2 weeks ago, and I asked him if he remembered Francis Allotte, and he did. And he confirmed that he completed his PhD at Princeton under the supervision of Professor Hopfield. And not only that, he recalled how Francis had made a tremendous contribution to Ghana through teaching and curriculum development and raising the visibility of Ghanaian and African physics internationally through different organizations. So Francis's impact really goes from young students right up to recent Nobel laureates. But getting back to the history again to finish up this story, because there are a few more interesting points to make. The different models of quantum mechanics being proposed by Schrödinger and by Heisenberg and Born were not totally compatible. Although mathematically it was shown they were equivalent, there were different interpretations. And there are some wonderful quotes showing just how direct and uncompromising they were at criticizing each other's work. Heisenberg wrote that Schrödinger's interpretation was rubbish, and Schrödinger called the statistical probabilistic ideas coming out of Göttingen from Born a statistical obscenity. So anyone who's ever interacted with physicists knows that sometimes we can be quite direct, and it's, well, there's 100 years of history to show that things haven't changed very much in that way either. Work still carried on, and the mathematics got even more complicated with Paul Dirac, but with the use of 4x4 matrices, we start to show the consistency between quantum mechanics and special relativity. And this was an idea of a unified approach that also led to its own new predictions of the existence of antiparticles and the birth of particle physics as we know it today as well. In terms of these questions and debates between Schrödinger and Heisenberg, or between Einstein and Bohr, they were concretized in a 1935 paper by Einstein, Podolsky, and Rosen, discussing the fact that what physicists described as local realism was inconsistent with the predictions of quantum mechanics. And although we might not like that, all the experiments to date have shown that this is indeed the case, and it was for that reason that Aspey, Zeilinger, and Clauser won the Nobel Prize in 2022. And I'm showing this picture of Alain Aspey because he is also a very good friend of ICTP and has visited at many times in the past to support schools and lectures and other workshops. It was also while preparing this talk that I read this article written by Bill Phillips and Jean Delibar, which is essentially a commented interview with Aspey from 2023. And this is a wonderful article, and I strongly recommend, if you're interested in the history of entanglement, that you read this, because it not only gives the history of Aspey and Bell and Aspey's learning of quantum mechanics from Messier's book and Claude Cohen-Tanuji, but it also makes a link that I was unaware of with a talk that Aspey gave when he was very young in front of a certain Richard Feynman. And Feynman's own paper from 1982, which discusses the idea of why he continues to investigate aspects of entanglement and inconsistencies in the foundations of physics and quantum mechanics. We're still asking these questions even today, and it's been wonderful to see this year just so many fantastic explanations of the intricacies of quantum interpretations and how things are still making progress. So this is concluding the talk with a summary, I guess, of what I call the 3 ages of quantum. So quantum zero is the very early work up until the Bohr model. It really is just getting some idea, 100 years of experiments from Fraunhofer lines to an explanation of the Balmer spectrum. Then with the development of the complete theories after 2025 and the ability to do calculations and extend it to solid state materials, it was possible to develop the technology that essentially built 20th century society. Laser, nuclear power, transistor, semiconductor, electronics. And now we're moving into quantum 2.0. This is the field where the correlation properties of quantum states and entanglement can be applied in areas of computing, cryptography, and sensing, and more, known and yet to be discovered. Now, there are different ways of developing the quantum 2.0 technology, trapped ions, neutral atoms, superconductivity, and these have huge investments. But from a cost-effective perspective, maybe I'm biased as well, photonics is the system that I think where things just have such potential because it's already integrated within our communications networks, and it's also very inexpensive to develop training programs in quantum optics and quantum mechanics based on photonic technologies. I'd like to acknowledge the work of the German Physical Society in preparing a wonderful website called quantumhistory.de, from which a lot of the material in this talk has been taken. And in case you're interested in a general poster for your laboratory or office, if you just Google SPIE Nobel Prize poster, the Scientific Society SPIE developed a very nice timeline of all the Nobel Prizes involving light, masers, lasers, and so forth. And I was lucky enough to be asked to consult on that project and just check it for the details. So that's a very nice, attractive thing for the walls. Students love looking at it. So just let me close with a few points. There's clearly a lot to celebrate over the last 100 years. Teaching history, understanding history is invaluable, not only from its own right, but also if we are to convince decision makers of the importance of long-term research, we need to know the arguments to convince them of this. It isn't enough just to say because. We have to give specific examples. And I think the concept of quantum science and technology such as the laser and the internet provide all the arguments we need to convince decision makers of the need to support fundamental research and applied research. Long-term research and short-term research. We need them both. Francis Alote understood this very well, and thanks to him, we have a chance this year with the International Year of Quantum Science and Technology, and every year with the International Day of Light, to keep making these arguments and points to new audiences and to keep making change. So thank you very much for your attention, and I'll be very happy to take some questions coming online shortly. Thank you.
Hey, thanks, John. That was really great. Really great. I'm sure there's lots of questions here. And I don't see you yet, but okay. Question.
Can you hear me?
Yes. So where's the question? Oh, okay, I got a question over here. Oh, there you are. Where'd you go?
Joe, you'll have to relay the questions because I can't hear anything.
Yeah, thank you very much. Thank you for the very enlightening presentation. I realized that you took us through a vertical and horizontal presentation of the work of Professor Alote, which is very good. But one thing you said that caught my attention is the fact that you said physicists are direct. And probably I'll say it is because they are not social scientists like some of us. We tell our master's and PhD students not to be so direct. Because, for instance, you made mention of Heidelberg to Paul, saying that his work was rubbish. I thought that was a bit, too direct. What would you suggest to those of us who are here, even for those who are actually not social scientists, but physical scientists? Should they really go on that trajectory? Because that is not a very good thing to do. We need to show respect to our colleagues, no matter how much we disagree with their work and all that. So I'd like to take, or know your take on something like that. Is that a way to go, even if they are not social scientists? Thank you very much.
Thanks for the question, and thanks for the chance to come online at what is a wonderful event you're having. I couldn't resist putting that in because it reinforces the stereotype that physicists have in particular of just being rude and direct. I think that was 100 years ago. And I think that we've learnt a lot since then about the fact that it just isn't productive to be rude and direct, let alone whether or not we can argue that generations are different and so forth and all these social comments that are being made. I just think it isn't helpful. I think you should be professional and respectful in your interactions, but even it is difficult because sometimes telling a student who may have worked very hard on a problem that it's wrong, and in a sense, that time, they feel they've wasted that time. And our job is to say, well, it's not wasted, it's time that you've spent, you've learnt things, you've progressed in other ways. And I think we have learnt how to do that a bit better. I think physics still has a way to go because we can still be a bit too direct even today.
Okay. Another question I'm looking at here. Okay. I just got to do a little exercise. I'll get right there.
Okay. Thank you so much for the presentation. It was really insightful. My question was about what you predict the third wave of quantum physics would look like, the future of it. Because at least looking at the zero edition of it and walking through the first and the second, it almost feels like we are building on what was present to leap towards future development, as is the case with almost all scientific disciplines. So building on that foundation, what do you predict, if you can even, if it's possible to predict, what the future of quantum physics will look like in the third wave?
Well, the good news is that you will be able to see it. Because if you look at the timescales between the discovery of radioactivity and the development of nuclear power, or the theory of the photoelectric effect and the development of laser technology, you generally talk about a 50-year period between the beginning of one of these quantum eras and the real applications. So if you think that the beginning of the quantum 2.0 is now, it's only going to be in 50 years that we're really going to see the true benefits. So you'll definitely see that. I won't, but that doesn't matter. I mean, the main thing is that science progresses and technology can be used to help us. Now, the Alain Aspect, in the opening of the International Year of Quantum in Paris, was asked a similar question. And he said that he thought the real application that he foresaw for quantum 2.0 was in quantum sensing. He was less optimistic about quantum computing and quantum cryptography because there were other ways to do this. But the sensitivity advancement you have using entangled states and sensing is something that's very concrete, and it can really help in practical measurements that we can make for healthcare, agriculture, and so forth. So I think the sensing is the place to be.
Okay. Another question? By the way, I think there's lots of excitement already in Quantum 1.0. In fact, it seems like we're just sort of getting into stride, right? 10 years ago, we were celebrating a century of photonics, so I think that's still going on, and there's plenty of excitement. Any other questions here? Do I see no students? Anybody online? Okay. Well, oh yeah, I got one down here, okay.
Thank you very much, Prof, for the wonderful presentation. You have really demystified quantum science and technology. My area of concern is technology transfer. How do we transfer all this high-tech transfer to our continents, especially IC, integrated circuits, some high-tech technology? How do we transfer them to this continent so that we can also bridge the divide between the advanced country as well as developing country in our continent? Thank you very much, sir.
That's a question that many people have tried to address, including Francis Alote, for 50 years. And it's, I don't know, I don't really know the answer in the practical sense, because this involves a lot of government initiatives with regard to intellectual property and international law and so forth. What I can reply to, I think, is my own field, which is really education. And I think that the key to any area of ensuring that Africa benefits from the technology is to make sure that the young people are trained in the technology, so that there is a highly trained workforce in place ready to adopt anything that is available. And it's that training aspect which I think is something which is where the answers are very clear. It's just a question of funding and of the organisation. Events like this are part of it, but if you see what an organisation like ICTP has already achieved in Africa, or the initiative like AIMS for mathematics have already achieved in Africa, imagine what they could do with 20 times the budget. It's a very simple thing. We know that these things work. Increase the budget and they will do a lot more. And that will help the education side. And I have every trust in young people that if you have educated, smart people and they see what's on the horizon, they will find solutions to do things. Speaking of education, the one thing I can say is that these slides that I showed, I'm perfectly happy to give them away to anyone who wants them and use them in their own classes or their own talks during this quantum year. So we need to share as much as possible and make science as open as possible. So just contact Joe, who's the chair, or just send me an email. I'm not hard to find, and we'll be happy to share the content of today's talk with you.
Yeah, well, that's a wonderful offer, John. That's a great message for us. You know, this has been a wonderful start, inaugural lecture for the Latte Lecture Series. So let's thank John Dudley, Professor Don Dudley again.
Thank you very much.